I pushed the record button. Okay. So Chem 8, fall 20. I'm just going to write down the name. 10/29, right? Today? 2 days before 29, yeah. 10/29, 2020. Okay. And we are discussing alkene chemistry. Alkenes. All right. So when you look at an alkene, okay, this is propene. This guy is propene. Okay, this is the pi bond. One of the two bonds in the double bond is the pi bond, and the pi bond is the bond that's made by side-to-side overlap. Okay, so when pi bonds see something that's electron deficient, okay, I talked about it in the Monday, Wednesday, Friday class on yesterday. I will briefly talk about something that, so maybe on the right side, we can do like a little quick review. So we have seen molecules such as CH4, okay? We have seen compounds such as NH3, okay? We have covered it in the past. We have seen a bunch of compounds made out of small, like the minimum number of hydrogens and minimum number of other elements, making covalent bonds.
The board, oh, sorry, the board is blurry again.
Okay. I thought we could trick it. Pushing the wrong button. Okay. Okay. CH4, NH3, OH2 with two lone pairs. Okay. We have seen these molecules in the past. Okay. We have also seen another molecule, BH3. And we found out that even after boron makes 3 bonds with 3 hydrogens, it's still not happy. Is it reflecting too much, or it's okay? If it is a problem, let me know. If it is not a problem, then you can maintain your silence. Okay, so we have seen these compounds. One compound that we haven't talked about, in the periodic table, it's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. I haven't showed you any compounds with the halogens and the hydrogens. So if we look at those compounds now, if we look at molecules made out of fluorine and hydrogen, chlorine and hydrogen, bromine and hydrogen, or iodine and hydrogen, okay? Essentially, I wrote them in the wrong direction, essentially HF, HCl, HBr, and HI, okay? They like to get rid of their hydrogen. They're all strong acids. They're all strong acids.
Sorry to interrupt you, but the screen's blurry.
You're not interrupting. You're doing me a favor. You're doing us a favor. So don't be apologetic. You guys are extremely polite. I appreciate that. Don't be so polite. People are going to take advantage of you guys. I mean, when you know that something is not right, just speak up. Don't be too polite like our son. Sometimes politeness can be annoying. I had a friend like that. I'm not going to talk about that. Let's talk about chemistry. Strong acids, an acid, what is so special about an acid? Acid produces H+. Acids are known for, they easily produce H+, which is nothing but a hydrogen atom with no electrons whatsoever. Okay, this is how hydrogen is produced. Hydrogen is born with 1 proton and 1 electron, right? Atomic number 1. When this is missing, if this is gone, okay, if this is gone, what are you left with? You're only left with a proton. Therefore, H plus is often referred to as a proton. So this guy is a proton. Okay, acids produce proton because once it produces a proton, whatever else is produced on the other side of that species is a negatively charged species, and it's a happy species. Let's see, let's check it out. Let's check out this guy. This is called equilibrium arrow. That means the reaction as it splits into H plus and the F minus, the backward reaction is also happening. You know, I'm losing my proton, I'm becoming the proton and me without the proton, but then those two guys are also combining back to form the whole Shantanu. It's kind of going back and forth. Okay, so as this thing happens, if these are the electrons from fluorine, and if this is the electron from hydrogen, the bond breaks in such a way, the bond breaks here. Okay?
The board is blurry again, sorry.
Okay. No, sorry. Sorry is not needed. It's probably going to take us like few cycles. Okay, so the bond breaks here, and the fluorine gets to keep all the electrons. And you produce the hydrogen with nothing, 0 electrons. Therefore, this is plus, and the fluorine now has an extra electron, because that's not how fluorine is born. Fluorine is born with 7 electrons. This is how a normal fluorine atom is born. Okay, 7 electrons. All of them have 7 electrons. Fluorine, chlorine, bromine, iodine. We have covered it in the past. Now it's got 8 electrons, and therefore it has a negative charge. But by doing this business, fluorine feels like it's looking like neon, because this is exactly how neon looks like. So it feels like neon. And that's the incentive. That's why they do that. So it's called, as an acid splits into a proton and its anion part left over, this anion is often called a conjugate base. Why is it a base? Because the definition of acid, the simple definition of acid is something that produces H plus. What's the definition of a base? Something that can accept a proton or H plus. Something that can react with a proton. Because it has an extra pair of electrons, it can react with a proton and it can regenerate HF. So it goes back and forth. That's why we write a half arrow here, this direction, and a half arrow the other direction. Okay? So the bottom line for this discussion, the reason that we are having this discussion, well, this discussion was to remind you of the different compounds. Then I talked about another type of compound that goes with that list: hydrogen with boron, hydrogen with carbon, hydrogen with nitrogen, hydrogen with oxygen, finally hydrogen with the halogens. Okay, and those guys are pretty strong acids because of another reason. Number one, once the hydrogen is kicked out as a proton, it produces something that feels like an inert atom. Okay, that's one thing. Another thing is they are very electronegative. Fluorine is the most electronegative element in the periodic table. The value for, if you remember, the value for carbon, electronegativity values for hydrogen 2.1. It might ring a bell. We talked about it in the past. The number for carbon is 2.5. The number for nitrogen is 3.0. The number for oxygen is 3.5. For boron, I don't remember. 1.9. I'm not 100% sure. It's less than hydrogen. I think it's 1.9-ish. That number for fluorine is 4.0. That's the biggest number, electronegative number. So the fluorine, being very electronegative, it likes to pull the electrons in the bond toward itself. It's extremely greedy for electrons in a bond. Okay, that's the definition of electronegativity. If you go back and read or watch the videos, that's what was going to turn out. Okay, that's that. So they're all chlorine is 3.5. Bromine maybe 3. I'm not sure. I'm not 100% sure. Okay, they're all kind of pulling the hydrogens toward the bond between chlorine and the halogen and the hydrogen toward themselves. Therefore, they all like to split and make H+. Okay, so with that information, let's come back here. So we're going to start using HCl. We're going to start using HCl as a reagent. Okay, and you know that HCl, like HF, will like to break this bond and produce Cl- with 8 electrons around itself, and H+. Okay, just keep this in mind. This is very important. HCl, HF, HBr, and HI, they form H+ and the corresponding anion. Corresponding anion is often called the conjugate base because it acts like a base. Base is something that can pick up protons, that can react with protons. Okay, so when this is going to be your first reaction of an alkene. So when this guy, let's write down everything. There is a carbon here, okay? There is a carbon here. I'm going to just like write down everything around the double bond. And this guy is propene. Okay, this E is important. What else is around the double bond? The hydrogen and 2 hydrogens. Okay, so and this is the sketchy bond. Remember that this is the sketchy bond. This is the pi bond. The red bond is the pi bond. Okay, so when an alkene is facing one of these acids, HF or HCl or HBr or HI, something terrible happens to the double bond. If you react it with HCl, okay, HCl produces Cl-. I'm not going to write down the electrons, and proton. Okay. Once you throw in propene and HCl in a container, in a round bottom flask, and maybe heat it up a little bit, and they're floating in some kind of a medium, like some kind of a solution, some kind of a solvent. Once that happens, and HCl is becoming H plus and Cl minus, the double bond doesn't like to be the double bond. I told you that the double bond, the pi bond, is the most vulnerable part of an alkene. So what it does is like a little gecko picking up a fly, like, you know, it sticks its tongue out and picks up a fly, exactly like that. This is, imagine that this is the tongue of an alkene. So it opens up its tongue and grabs the proton, okay? So this entire bond breaks. How does it break? Well, I'll show you. This bond opens up. Imagine that this is the bond. So it either opens up this way or it opens up this way, okay? Like a gate opening. The gate can, you know, imagine that you have a gate in your periphery around your house, and the gate is designed in a very cool way. The gate can open this way or the gate can open this way, okay? So the gate can open up, okay? There is a hydrogen here, there is a hydrogen here, there is a hydrogen here. Let's say that it opens up to the right first, okay? To this direction, it opens up, and imagine that this electron is here and this electron is here, okay? Just follow everything the way I'm doing it, okay? And it picked up this hydrogen. It picked up this proton. Let's put like a little square around it so that you know that this is this guy. It picked up the proton, but in this process, as the gate opened up, as the gecko stuck its tongue and picked up the little bug, it deprived this carbon, the carbon in the middle, of electrons, because now this guy doesn't have access to this electron anymore. So as it picked up the proton, this proton is happy because it got an electron, but this guy got screwed up. This got the short end of the stick, okay? Now this proton is now positively charged, and this is called a carbocation. This is called a carbocation. Carbo, because it's carbon, it's a positive charge on a carbon, okay? And you know that positive is cation and negative is anion. Okay? So this is a carbocation. Okay? This guy is a carbocation. Okay? Realize something interesting, that as this carbocation has formed, you could have also made the other carbocation. What would that be? That would be if it picked up the proton here and formed the carbocation here. Let me show it to you and then it'll make more sense. The other carbocation would look like this. All the body parts of this original molecule is pretty much the same. Instead of this bond hanging from the terminal carbon, let's open it up to the middle. If it picked up the proton, if the gecko picked up the proton in the other way, with the round electron here and the cross electron here, and it picked up the proton here, okay, this is the same guy. This is the proton that came in as a proton, but now it's not a proton because now it's got an electron from that double bond. Now, who got the end of the short end of the stick? Well, this poor guy. This poor guy is now a carbocation because it has been deprived of electrons. It's supposed to have 4 electrons, 1, 2, 3, and 4, but you took that bond away. You took that pi bond away, so this guy is positively charged. Okay? What happens as a next step? Well, is the carbocation is going to hang out for eternity until the for 100 years? No. What else is there in the system? Well, after HCl became H plus and Cl minus, Cl minus is hanging around, right? Cl minus is in the vicinity, and it's got an extra electron that makes it negatively charged, okay? And it's the same deal here. You have Cl minus hanging around this guy as well, okay? And it's got an extra electron, even though Cl minus feels like neon, it would rather not be looking like neon, and it would rather like neutralize itself. Nobody wants to be charged, okay? Every species likes to be neutralized. So how can it neutralize itself? Well, what if it makes a bond here by attacking the carbocation center with one of its extra lone pairs? This is an abnormal lone pair. Chlorine is not supposed to have a fourth lone pair. It's supposed to have 3 lone pairs and 1 electron. That's the way chlorine is born. That's the way fluorine is born. That's the way bromine is born. That's the way iodine is born. But in this case, it's got an extra one. So if it uses that extra pair of electrons to form a bond between carbon and chlorine, it'll form a brand new bond, and everybody is going to be neutralized. The carbon is going to be neutralized from this having a bond like a normal bond, like a regular average organic molecule, covalent molecule, and chlorine will be getting rid of 1 extra electron. It's going to be happy. And same thing can happen here if it attacks this carbon. And let's see what happens here. Okay, so when this guy does that reaction, I'm using color coding, and I'm urging you, I'm begging you to kind of work it out on a piece of paper, if you have a little board on your wall, or find some surface and work it out. Practice it. This is the first chemical reaction. I'm showing it to you, and it might be overwhelming. Okay, it might make sense when you're watching me do it, but it's not that simple. Okay, so double bond, one of these acids, it breaks into proton and the anion. The pi bond picks up the proton. The proton can stick to the right side of the double bond, producing a carbocation here, or the proton can be picked up on the left side of the double bond, producing the carbocation here. Okay, one of them is more stable. We will talk about that. After the carbocation species is produced, 1 or 2 carbocation in the middle or carbocation at the end, the Cl minus, the conjugate base, this is the conjugate base. Okay, that's the conjugate base. The conjugate base can attack the carbocation with its extra pair of electrons and form a legitimate organic compound again. I'm following all the color coding, so it should not confuse you. But you need to practice. If you do not practice, it's not going to work. Okay, I'm trying to keep everything the way we started out. Okay, and the chlorine is now stuck here. This electron is from chlorine, and that blue dot, the Blaupunkt, there is to be an audio manufacturer from Germany called Blaupunkt, means blue dot, is now attached here. So this is a legitimate compound. Everybody is neutral. The carbon has gotten an electron, and so it feels like a normal carbon. It's not positive anymore. The chlorine is now having only 1 electron in its outermost shell, because this is its outermost shell. You count 1 electron in the bond. 1, 2, 3, 4, 5, 6, 7. It's neutral, and it's a legitimate molecule. So this is called an organohalide or halogenated compound, alkyl halide. So what does it look like if I don't draw the hydrogens? This is what it looks like. This is same as This is same as that. And this guy is called an alkyl halide. And it has a name. So you just learned how to make an alkyl halide from an alkene by reacting it with an acid. This is very cool, okay? This is your first exposure to a real reaction. And what will this molecule look like? So that's one molecule that's produced in this reaction, okay? That's one. And the other one will look like this. Let's shorten the arrow so that I have more space to work with. Carbon, carbon, hydrogen, hydrogen, hydrogen. This is how the alkene came as. Well, there is a hydrogen stuck here. Let's write that down with all the color codings, which takes up a lot of time for me, but I prefer to do that. This is the hydrogen that came from HCl, okay? And this chlorine has attacked here. So therefore, the chlorine is attached here with all its electrons around it. The 3 lone pairs chlorine was born with, and the stolen electron from this proton. This electron used to be here. This electron used to be on the chlorine, on the hydrogen, right? So now this is another legitimate molecule. And what does it look like if I just get rid of all the hydrogens and do like a skeletal diagram? Well, this is what it looks like. This is another alkyl halide. This is alkyl halide number 2. Alkyl halide 1 and alkyl halide 2. So if you remember that the double bond used to be here. Okay, I'm not going to draw it. The double bond used to be here, and the double bond used to be here. All that happened is the double bond disappeared, the double bond became single bond, and the chlorine got stuck with the hydrogen on the other side. All you did is added, if this is the double bond, imagine the double bond is right in front of my chest. So the chlorine got attached here, and the proton hydrogen got attached here, or vice versa. Chlorine got attached here, and the hydrogen got attached here. So you're basically adding HCl across the double bond and erasing the double bond. It's that simple. It's very easy. Okay? Take a look at the reaction. You need to practice. If you do not practice, all I expect you to do to prepare for the next quiz, whenever that happens, is go home, or whenever you're already home, just practice what we are doing in the lecture. Watch the video, try to repeat what I have done, and then close your eyes or close your video. Don't look at it, and see if you can pull it off. Exactly what we have done in the lecture. Okay, I'm going to keep the exams very straightforward and simple. Take a look at it. I'm going to take a picture and go to the next topic. This is pretty intense for you guys. You might feel overwhelmed. So I really, I'm urging you guys to pay attention. If you guys have been doing very well so far, this might be the time when you need to put extra attention. This is a real reaction that we just talked about. Okay. When you look at the picture, make sure you understand the flow of reactions. And this is called mechanism. Mechanism means this whole thing that we have done here, showing how product or products form from starting compound with arrows pushing electron or electrons. I'll take one more picture and delete the previous one. Pushing electrons is mechanism. That's what is mechanism. Mechanism is nothing but how you think the reaction is happening. Well, this pi bond is opening up and reaching out for the proton in the HCl. How do we show that? We show it with an arrow starting from the middle of the bond and ending on the proton. That means this bond has opened up. It has gotten loose from this end or this end. If it got loose from this end, then that happens. If it got loose from that end, then this happens. Then what happens? Well, then you have Cl minus hanging around. The Cl minus attacks the carbocation here or here and produces two different alkyl halides. That's what they look like. In one alkyl halide is looking like that, another alkyl halide looks like that. We will learn how to name the alkyl halides, but not today. Okay. Let me take a picture, and I'm going to delete the other picture because I've written the definition of mechanism. This is gone. Let's take a new picture. Okay. Let's keep moving. Okay. So old chemistry, old molecules, sp3, just to remind you, sp3, 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 even the fluorine is sp3. It looks like a straight molecule. It doesn't look like not even close to a tetrahedron, but it's sp3, 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 sp3. The difference between these guys from those guys is that you are dealing with elements that are very, very electronegative, and it's just one of them is attached to the other guy. So once the proton is snatched away, it's plucked, you produce like a nice little one single element with an extra electron that makes it think like it's almost looking like the inert atom in that series. Fluorine looks like neon, chlorine looks like argon, so on and so forth. Okay. So that's what we discussed here. Then we discussed how a double bond can react with one of those acids and basically attach the acid H and Cl across the double bond. Let's practice a few reactions, and I'll also tell you which one is a major product and which one is a minor product. I'm not going to dwell a lot on that. I usually spend a lot of time talking about carbocation stability, but I'm going to cut that discussion to the minimum. Okay, I'm going to erase the board. If you're feeling overwhelmed, it's natural. You need to practice to get rid of that overwhelming feeling. If you're feeling fine, then you're doing good. Just make sure that you're not complacent or you're not fooling yourself. Make sure that that confidence is actually well-founded. You are supposed to be confident. Because even if you understand what's going on right now, if I ask you to reproduce it, you may have real hard time. I'm actually thinking about offering a review before the next exam, not the next quiz, because I think it can help. Even though I was kind of disappointed that only like 4 students showed up from the 2 classes before the previous exam, the first exam. I was thinking that maybe you guys don't need it, but then I'm going to offer it. If nobody shows up, nobody shows up. I'll hold the review even if like 1 person shows up. All right, so this reaction where an alkene, so I'm going to just cut the fluff and just show you the chemistry. One color reacts with HCl. Okay, what's the product look like? How do you draw the product? Very simple. You draw the alkene. Don't draw the alkene. Okay, get rid of, wipe the double bond. Wipe the double bond, add hydrogen. Maybe we should color code this guy. I'm going to use a different color code. H, let's put HF, something different. Let's put HF, hydrofluoric acid. When you are adding hydrofluoric acid, well, hydrofluoric acid can add to the double bond in two different ways. One way, hydrogen is attached here, and the fluorine is attached here. That's one. We just went through it. We just showed you the mechanism, and I showed you exactly how it happens. All I'm doing right now is showing you like what how do you like pull it off if I'm not asking you about the mechanism. If I'm just asking you to predict the product, how do you pull it off? Plus, you make the other molecule, again, you don't draw the double bond, and you add the proton to one side and the fluorine to the other side. In this time, you do it the other way. You add the fluorine in the middle and add the hydrogen to the end. That's it. So if I don't draw the hydrogen, what does the product look like? If in one color, the product looks like this. That's it. That's simple. Which one is major and which one is minor? There is a rule. The rule is called, I always forget this rule. What is that rule? Isha, are you here?
Yes.
What's that rule? Not McDonald's rule. What is that rule?
Markovnikov.
Markovnikov. Sorry, thank you. Markovnikov's rule is Markovnikov. Markovnikov's rule, I'm just going to say the rule in simple Bengali, not Bengali, Bengali is my mother tongue, simple English, okay? It says, this is the anion, right? That it came in as F minus, okay? That's the anion, not onion. I hope my pronunciation is not as bad that you think, oh, Dr. Maitra is calling F minus as an onion. Okay. The anion, green doesn't look very good. Let's keep writing with the black. The anion attaches to that end of double bond it's a kind of a convoluted sentence. Forgive my bad English. The anion attaches itself to that end of the double bond, which has less hydrogens. Read this rule and tell me which one is major. Let's say this is 1 and this is 2. This is 1 and this is 2. So read the Markovnikov rule. Markovnikov rule says that anion F minus or Cl minus or iodine minus or bromine minus, it goes to that on the end of the double bond. It likes to go here or here. It prefers that end, the end that has less number of hydrogens. So in that case, that's going to be the major product. So is 1 a major product or 2 a major product? Figure it out. This end has which one is major product according to that rule? Vincent. The anion likes to attach itself to that end of the double bond, which has less number of hydrogens in the original alkene. If that's the guideline, is this the preferred product, or if that's the preferred product? Come on, guys. I came up with an idea yesterday. I'm going to tell you guys that after somebody answers this question.
Two.
Excellent. Watch the video and figure that out. Why this is major and why that's not major. Okay. Okay. Now I'm going to tell you what I came up with a resolution. You guys won't like to hear it, and this is not like a I'm taking revenge on you or anything like that. I had a moment of my internal unrest that kind of got exposed to the students. I almost got pretty little annoyed because I was asking a question and nobody turned on their cameras. It's too late probably right now. It's not going to help you. So I decided that at the end of the semester, I'm going to watch the videos, and on an average, like right now, I can see only one person who is Alexa having the camera on, okay, and participation. So based on most participation, I'm going to come up with my own algorithm and my own rule. Those who have historically, like consistently kept their cameras on in the lectures, I'm going to watch the lectures, glance through the lectures in the beginning. At the end of the semester, when I have nothing else to do, better to do, when I'm bored, I'm trying to kill boredom, I'll do that. And those of you who have consistently kept your cameras on and participated, I understand you have computer problems, but you cannot have computer problems, cannot be a prevalent problem with 45 of you, okay? Maybe a small percentage. Those of you who have been keeping your cameras on and you have been participating, I'm going to give you guys a bonus point. That has nothing to do with the syllabus. You can say that, oh, Dr. Maitra is being unfair, changing the rules. No, I'm not changing the rules. Every rule is same. I'm just going to add points, bonus points, to those of you who have been participating. And for class participation, you might accuse me that, oh, he didn't talk about it, then I would have kept it on. But I mentioned that when you keep your cameras on, when you participate, you're actually helping me motivate myself. So, it's kind of like empathy for fellow human beings. So those of you who have been doing that, I'm going to add some bonus points. I don't know how many. It could be 1, it could be 2, it could be 3, it could be 4 or 5. It can make a difference for your grade. So anyway, I just thought I would share that information with you. This reaction is called, so whenever you have, before I tell you what this reaction is called, let me tell you what's an electrophile or what's a nucleophile is. Okay, there are 2 words I'm going to introduce. Word number 1, it's called electrophile. Electrophile means something that loves electron. This word phile is loving. Okay, electrophile means something that likes electrons. That means somebody who is suffering from lack of electron density. So when you are dealing with an H plus, and it becomes F minus, this H plus is an electrophile. Okay, because it's suffering from electron density loss. It wants to be hanging out with electron density. Okay, somebody who is not having enough electron density, like a cation, is an electrophile. Okay, all cations are electrophiles. And the other word is nucleophile. Nucleophile, a lot of new terms, you guys better study. Nucleophiles means something that loves nucleus, okay? That means nucleus loving. This basically means electron loving. Okay, electron means negative charge loving. Nucleophile means nucleus loving. And nucleus is nothing but positive charge. Okay, so these guys themselves, these guys have extra electron. They have extra electrons in themselves in different forms, like anything that has a lone pair. Okay, anything with lone pair falls under this category. Anything with lone pair or negative charge, they are all nucleophiles. Okay, so we learned two new terms: electrophile, electron loving. They are generally cations. You know, it's not very well written. All cations. All cations are electrophiles. Anything with lone pair, anything with negative charge is a nucleophile, because they are looking out for dissipating their negative charge or helping someone with their lone pair. So they are nucleophiles. They're nucleus loving. So don't swap the concepts. When I was much younger, many years ago, 3 decades ago, when I was learning organic chemistry, I used to accidentally always interchange the meanings. I used to mean nucleophile as electrophile and electrophile as nucleophile. Okay, so electrophile and nucleophile. So when this reaction is involving an electrophile, this reaction is called electrophilic. The name of this specific reaction is called electrophilic addition, because everybody is staying. This guy is staying, it's not losing any body part. Hydrogen is staying from HF, fluorine from HF is staying. So everyone is being accommodated in this reaction. It's like an invader invading India and then making our country their country. Just decided to, this looks pretty good. I'm going to just not go back to my own country. I'm just going to settle down and have my families grow through generations, making hybrid products. Okay, so that's how an addition reaction is defined. Electrophilic addition reaction of what? What kind of species? Of alkenes. This is the name of the reaction, electrophilic, because that guy, electrophilic, what kind of reaction? It's an addition reaction. You will see substitution reaction pretty soon. Electrophilic addition reaction of what? Alkenes, because you're doing the reaction on an alkene. Okay, electrophilic addition reaction of alkenes, and that's the major product, that's the minor product. I usually spend like 2 or 3 classes on carbocation stability. We can't do that luxury right now. I'm going to erase and I'm going to talk about a few more reactions. 122, not bad. Once I take the picture, I'm going to erase the board and go for the next round of discussions. Watch the video repeatedly, go back and watch other videos. You can watch them at higher speed. You know that 1.5, 1.25, 2.0, and glance through them, make sure you understand everything. You can put all the concepts together. It's sequentially learned and sequentially used, because what you learned yesterday, you need it today. What you learned today, you need it tomorrow and day after. Okay, you can't forget. You can't learn it blockwise and do well. In order for you to do well in the exam 3, you need to understand what was discussed in the past. Okay, so This is an electrophilic addition reaction of an alkene. I'm going to show you a few other reactions. I'm not going to talk about their mechanism. I'm just going to show you like this is what happens. This is what you cook, and that's the product. How the ice cream forms, or how the baking happens, or how you make the chili, we don't care for those reactions because it's just impossible to teach all the mechanisms, and it's not necessary for this class. I want you guys to know at least one mechanism, and this is one. I might or might not teach the second mechanism down the road. Okay, we'll keep it simple. Markovnikov's rule. Remember what Markovnikov's rule is. There, it's important for the quiz number 3. It's important for the exam number 3. It's important for the final. It's a big deal in the world of chemistry. I need to wipe the board up just a little bit because there are too many spots. So a few other reactions. So when we start with, let's use a different molecule. What's this molecule called? Name it. Figure it out. I'm not probably going to bother to ask you. Make sure that you can name it. Okay. This particular molecule. So you saw, you know what? Let me just start in the middle. Let's start in the middle. It's a slightly different molecule, but the same principles apply. The reaction that you have just seen is with, I'm not going to show the mechanism. If it reacts with, I'm just going to pick a different halogen now. Let's say instead of using HF or HCl, I use HBr. What will be the products? Well, one product and the second product. It's going to produce two different products. In one product, H is going to go here. In the other product, H is going to go there. And the bromine, the anion, is going to go here, or the anion is going to go here. Okay, so this is product number 1. This is product number 2. If I ask you, which product does Markovnikov rule dictate? The one on the left or one on the right? You guys think about it. Okay, this is an electrophilic addition reaction of an alkene. Electrophilic H plus addition, because everything is being added, nothing is getting lost. Reaction of an alkene, double bond. Another reaction. Think about which one is major, which one is minor, right or left, major. Okay. Second reaction. You have heard about hydrogen gas. If you use hydrogen gas with a catalyst, you need a catalyst, a metal catalyst. Metal catalyst can be platinum or palladium. Catalyst. No detailed discussion. This is important. This is a catalyst, platinum or palladium. When you do that, the double bond disappears and a single bond appears. What happens? Well, you lose the double bond and you add hydrogen across the double bond. So basically, you make alkane from alkene. That's it. So this is an alkene. Alkene becomes an alkane. This is like going back in history. Dad becomes grandfather. Okay, so hydrogen gas goes to that, and this is a different reaction, right? Electrophilic addition reaction of an acid. Another reaction, if you react it with, I'm just using different colors. If you react it with bromine, okay? Bromine gas. Let me just split the bromine into two colors. One bromine is, let's say one bromine is blue and one bromine is black. How will you draw its Lewis dot structure? Pretty straightforward. 7 electrons here and 7 electrons here. 3 lone pairs, 1 bond, and 3 lone pairs. Okay. If you add bromine to a double bond, what happens? Well, the double bond disappears. And the bromines get attached to the double bond in like a zigzag way in opposite direction. So one bromine, let's say the blue bromine, is attached down here, and the black bromine is attached up here. Okay, you get a dibromo compound. Again, the double bond disappears. You see that in all of these reactions, the double bond is disappearing, and you're forming something with a single bond. Okay, it's a substituted alkane. This is just an alkane. This is a substituted alkane. One bromine got in this case, 2 bromines got in. What other chemistry can happen here? The hydration. You can add a molecule of water across the double bond. How does that look like? How is it done? So the last reaction is you take the alkene and you react it with water, just simple water, but there is a little trick. I'll tell you what the trick is. You add water and you have to add a little bit of catalytic acid. So something like HCl, just a little bit, maybe a drop. 1 drop will do it. So you need H plus. Where is that H plus coming from? Well, H plus catalyst. That gets the reaction going. We don't need the details. You just need to know how the product forms. This can come from HCl, like dilute solution of HCl, like 1 normal HCl. You have seen it in the past. What does the product look like? Again, the double bond disappears, and you get 2 products. Okay, 1 product plus 2 products, second product. In 1 product, the water attaches itself here. In the other product, water attaches itself here. Does it follow the Markov-Nikov rule? Yes, it does. Okay, so the proton H plus gets added here or here. Let's do it one at a time. Let's say the H plus gets attached here, and in this case here, and the water gets attached here as OH. Water gets attached, and then it loses one of the hydrogens. Okay, just try to remember the reaction. So from water, only this part gets attached. Okay, it loses a hydrogen. That hydrogen gets regenerated as a proton. No details needed. So what do these products look like? They're actually alcohols. You can think about it. If I just draw them in 1 color, this is what they look like. That's this alcohol, and this is the other alcohol. Okay? Alcohol on the left has a branch from the carbon number 2. Alcohol on the right, the alcohol is at the end of the streak. Okay? This is 1 alcohol, that's another alcohol. All right? So this reaction is called, this reaction, as you see it, you describe it. So this reaction is called, very simple, acid catalyzed hydration. You're drinking water. All you're doing is you're adding water But this hydrogen didn't come from that water. This hydrogen came from the proton over here. But hydrogens are hydrogens, right? So you are basically adding H2O across the double bond. That means you are making the alkene drink water. You are hydrating the alkene. So this reaction is called acid catalyzed hydration reaction of an, alkene. Okay, if you're a little overwhelmed, it's time to sit down and study. You have to study. Ask your supervisor for some mercy. Ask your family for cutting you some slack. Figure out a way to study. Okay, I can't review everything every day. The reaction that I showed the mechanism of, electrophilic addition reaction of an acid across a double bond. This reaction is called hydrogenation. Hydrogenation. Okay, you are saturating a double bond with hydrogens. This reaction is often called, there is a sparrow, I think it wants to learn hydrogenation. Hydrogenation, you heard about hydrogenated fat, saturated fat. Unsaturated fat has double bonds. Saturated fat has no double bonds. Saturated fat is bad. Unsaturated fat can be a little better than saturated fat. We will discuss it some other time. So hydrogenation is also a reaction where you accomplish saturation. Saturate double bonds or double bond. You're saturating. You're saturating means you're sticking more hydrogens, no more double bonds. That's hydrogenation. This is adding a bromine or HBr or HCl or HF. This is hydration. You're making the alkene drink some water. This is bromination. This reaction is called bromination. Now you realize that this is our usual normal speed pace at which we teach. So now you can realize that at the beginning of the class, I had been going extremely slow, just so that you guys don't feel overwhelmed. I have to pick up some speed, not for completing syllabus, but you need to get used to it now because your foundation is already built. You are kind of like driving on the freeway right now. Okay, so bunch of reactions, only mechanism is needed over here. I'm going to take a picture. If you took this class from me in in-person setting, you will probably be experiencing something like this speed from day one. Maybe a little slower in the beginning, but not as slow as I have been doing so far. This pretty much ends our discussion with alkenes. Let's talk about alkynes. Let's learn some simple nomenclature, simple naming of alkynes. And it's pretty straightforward. It's not that difficult. So we learned how to name alkenes, how to react alkenes, their shape, their hybridization, bond angle, blah, 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 all of that stuff, right? So now let's talk about alkyne. And the good news is that we have already been exposed to their hybridization, their shape, how many pi bonds, how many sigma bonds, all that stuff. It's not going to be that bad. And the chemistry is surprisingly similar. It's pretty cool, actually. The board with the spot. I'm going to name my board Spotty. I'm sure there are Dalmatians that are called, they have their name Spotty. Let's spend a little time doing a nomenclature of alkynes. Pretty straightforward. Okay. Now we are in the area of alkynes. Okay, smallest alkyne, well, you know what they are. This is the tiniest alkyne. Very quickly, I'm not going to ask you guys questions. sp2 or sp3? None of them. sp. This bond is made out of sp and 1s. sp and sp. This pi bond is made out of 2p and 2p. This pi bond is made out of another set of 2p and 2p, maybe 2pz and 2pz, 2py and 2py. Okay? Shape like an axle, cylindrical. Okay? All right. Reaction, name. This guy is called, what is it called? What is missing? Not ethane, not ethene, but something else. Alkyne, kyne. What is it?
Ethyne.
Very good. What's this guy called? Count how many carbons are there. 1, 2, 3, and 4. Name it quickly. Answer, please. Lost?
Butane.
Butane.
What about this? 1, 2, 3, 4. That's also butane.
The
How
board
do
is,
you distinguish?
Professor, the board.
Thank you. Lost my pen. I don't think the camera likes to be in that corner. It was happening the other day. This is butane and this is butane. They look a little different. How do we distinguish between the two? Quick. If you don't answer in like 5 seconds, I'm going to write.
1-butane.
You need to be
Two
faster. Okay. Good. Okay. Sounds good. Where are we with time? 1:42. So, reactions. This is how you name alkynes. I'm going to ask you some simple questions about alkynes. I might stick like another function, another substituent, and you need to figure it out. So don't say Dr. Maitra is being so unfair because we didn't talk about it, but you know how to do that. This is important. So name it, number it in a way that you get to the triple bond first, and then figure out the branches. Okay, let's start with this simple alkyne.
Professor, it's a little blurry.
Okay, hold on. It really doesn't like me to go to that corner. Okay. What's this guy? 3 carbons. Hurry up.
Propine,
Propine.
which is 1-propine.
Can you have 2-propine?
No.
Then, yeah, it's not important. So there's a hydrogen here, right? I'm going to just draw the hydrogen. 3 carbons, so don't get confused. A triple bond has a carbon here, and that's a carbon. If I write out a hydrogen, that means it's not a carbon, it's a hydrogen. So what happens when you do the first reaction that we did on alkene? So if we react it with hydrogen, I don't know, hydrogen chloride, what will happen? Will it get rid of one of the two double bonds? Will it get rid of one of the pi bonds and attach itself? It's that simple. That's exactly what's going to happen. So now the sigma bond between the carbons will remain. One of the pi bonds will stay there. Okay. Now the bond the bond is not linear anymore. Okay. It gets bent now. It's bent because it's an alkene, 120 degrees. It's a flat molecule with 120 degrees approximately bond angle. The hydrogen has been picked up here, and the chlorine has been added here. Product number one, just like an alkene, you're adding the acid across the triple bond, you lose one bond at a time. And you also get the other product. Okay, again, if you're feeling overwhelmed, I can feel it. I can feel the force that you guys are probably not too happy at this point. That's my assumption. If you are doing very well, that's fantastic. You need to study, you need to watch the video repeatedly. That's how people read and learn. That's how I learned biology and biochemistry. I'm not really natural at it. Okay, 145. So when you do the electrophilic addition reaction on an alkyne, the first double bond reacts first. One of the two pi bonds reacts first, and then it reacts one more time and produces the other product. I think we're going to stop right now. We're going to catch up on our discussion on Tuesday again. Have a good weekend, and please study. Okay. Have a good weekend. Bye, guys.
Thank you.
No problem. Thank you.